Hi, this is Professor Fernandez. In this video, we're going to work on example 3.4 from Calculus 2 Simplified. So in this example, the idea is that we are going to find the area of the region between the graphs of these two functions of y, not functions of x, and bounded by these two y values. So figure 3.4 over here shows what's going on. So this requires a little bit of proficiency with thinking about functions of y versus functions of x. So let's talk about that briefly here in this graph. First of all, if x is y plus 1, sometimes you can just turn things back into functions of x to make life a little more, I guess, easy. To do that here, we can solve for y, and we subtract 1 from both sides. So y is x minus 1. That is this line right here, x minus 1, right? At x equals 0, y is negative 1. At x equals 1, y is 0. So this is the line x equals y plus 1 that we found is equivalent to y equals x minus 1. So if we go up here and we try to do that with this equation, it's a little more difficult, right? If I move the y over, I get 3 x plus 3. If I move the y over, I get x plus y squared equals 3. And then I move the x over and I get 3 minus x. Now, if I want to solve for y, sure, I would get a plus or minus square root of 3 minus x. A little more difficult, but we can deal with it, right? Root 3 minus x, that is this upper branch of this left opening parabola. And then negative root 3 minus x is this lower branch of the left opening parabola. So you can see that we don't always want to turn things back into functions of x because they make life a little more difficult. Sometimes with linear functions, it's okay, but with quadratic functions or higher, it makes life a little more difficult. So we want to cultivate this competency of understanding functions of y on their own terms. So let's just talk about how that happens over here. How could we figure this out? Well, first thing to notice is that y squared is never negative, right? So if I have 3 minus y squared, the largest x value is going to be 3, right? That happens when y is 0. So there we go. When y is 0, x is 3. So that gives us that point. And then I'm subtracting y squared. So as y becomes non-zero, I'm going to get some x value that's smaller than 3. So if I'm, for example, at y equals 1, then 3 minus 1 squared, that's 2. So that explains why there's a point here on the parabola. It also explains why there's a point down here, because 3 minus negative 1 squared is also 2. Okay, so you can see that x equals 3 minus y squared starts at 3, right? That's the point over here when y is 0. And then it subtracts from 3 to get 2, to get 1, to get 0 all along. Subtracts from 3 as y gets larger. So that explains this graph starting at 3, and then as y gets bigger, x gets smaller. Also, as y gets bigger negative, x also gets smaller. So that's how you get this left openingness. The parabolic nature comes from the fact that y squared is related to x, just like y is related to x squared when you have a parabola that opens up or down. So that's the sort of coming from the relationship of the square of one variable related to another. Okay, so hopefully that gives you some sense of how you might understand these two graphs here on their own terms as functions of y without needing to put them back into functions of x. And now the question that as posed is to find the area of the region between these graphs. So that's the shaded area here. Now, we'll talk later about how you would try to do this. If it were functions of x, it would be a little harder. In this case, it's a little easier. I'm going to zoom in here to this theorem 3.2 in the book, and you can pause the video and take a look at it for a minute. But long story short, if you know that you have two functions of y that are continuous on some interval for y, and you know that one function is always, in this case, to the right of the other, right? We're thinking again in terms, we're used to thinking in terms of functions of x. So if you see this inequality in terms of functions of x, well, it's y equals f of x and y equals g of x. So this is y values larger than some other y value. So this is like a function f of x that is above some other function g of x. but that's not what's happening in this theorem, right? This theorem is about the area between functions of y. So when I look at this inequality, what it's telling me is that there's some function h of y that is to the right of some other function s of y, right? So to the right. Okay, so that is certainly true in our example, right? There it is. This function is to the right of this other function, the linear one, on the interval that we're interested in, right? From this is y equals -2, y equals -2, and this over here is y equals 1. Okay, so in our case, this is the parabola that is to the right of the linear function. And we just determined that c is -2, that's the smallest y value, and d is 1, that's the largest y value. Great, and then it tells us the area between these graphs is this formula. So notice what the formula says. You integrate from the smallest y value to the largest y value, so in our case, -2 to 1. And you subtract, you do right minus left. So our right is parabola, our left is the linear. So if we go back here, the parabola is this one. So we're going to subtract. We're going to say 3 minus y squared. Subtract the linear, which is y plus 1. This is all in terms of y, so we're integrating dy. Great. So let's bring this over here now that we've got our integral and talk about how to evaluate this. All right, first thing I'll do is I will simplify things, right? So 3 minus y squared, I'll distribute this negative, so minus y minus 1. And then I can subtract some things off. 3 minus 1, that's 2, minus y squared minus y. Great. And then from here, this is a bunch of integral versions of the power rule, right? So the antiderivative of 2 is 2y, antiderivative of minus y squared, so add 1, divide by the result. Same thing for y, so add 1, divide by the result. And all of this fundamental theorem of calculus is now evaluated by from -2 to 1. So it turns out if you do the math here, you get 9/2. So now we can talk about, is this a sensible answer, or perhaps did we make a mistake somewhere? First thing to know is that we're calculating, supposedly, right, the area between these two curves, and that's this shaded region here. Area should always be positive, right? So that's kind of a public service announcement. You can't get a negative area. I can't tell you, paint the wall -4 square feet. Use -4 square feet worth of paint to paint the wall. Makes no sense. So the area should be positive. The number we've gotten is positive. Perfect, right? Area could also be 0, but then there's no area. Okay, so I got a positive number. Check, that makes sense. Second thing we might want to double check with ourselves on is that in fact we applied this right minus left thing correctly. In this particular example, the parabola was always to the right of the linear function, but you can imagine other examples where maybe they switch. Maybe the example, the functions do this. So over here on the right, you have this curve and the line, but over here on the right, you have this line, right? So the function on the right changes. Example 3.5 in my book talks about that if you're interested. Okay, so that's all I'd like to say about this. Last little thing that I mentioned about not areas as functions of y, but if you wanted to do this as a function of x, you would be thinking instead of right minus left, right? That's functions of y. For functions of x, you're thinking top minus bottom. So the same exact region, you would have to think, okay, and you're thinking as x goes from -1 to 3 here, that would be our interval, and then you're thinking top minus bottom. So the linear function is on top until you get to x equals 2. And then this portion of the parabola is the top function, and then this portion is the bottom function. So if you're going to do this problem, find the exact same area using functions of x, right? The ones that we talked about earlier in the video, you would have two integrals. This region where the top function is a linear one, and this region where the top function is this upper parabola. That's a lot more work, not to mention solving for these equations for x was a lot more work also early in the video. So long story short, competency with working with functions that are functions of y really helps sometimes if you're going to find areas of those functions. Great. See you next time.